On June 3, 2026, a machine buried 100 meters under the border of France and Switzerland found something that shouldn't have taken this long to find. Scientists knew it existed. They'd known for over 50 years. They knew its mass, its charge, even roughly how long it would live before falling apart. And it still took them until now to actually see it. This is the story of the Omega CC+, the last piece of a puzzle 3 generations of physicists have been chasing. Here's the strange part. Physics doesn't usually work like this. Normally, you observe something first, then build a theory to explain it. This time, the theory came first, and it was so good, it told scientists exactly what to look for before they ever found it. To understand why that's remarkable, you need to know what a baryon actually is. Baryons are particles built from 3 quarks, bound together by the strong force, the same force that holds atomic nuclei together. You already know 2 baryons intimately, because they make up almost everything around you, the proton and the neutron. Both are built from just 2 types of quark, called up and down, but up and down are only 2 flavors out of 6. There's also charm, strange, top and bottom. And if quarks really do combine according to consistent rules, then swapping in these heavier flavors should produce entirely new baryons, particles that don't exist in ordinary matter, but should exist somewhere if you smash particles together with enough energy. This idea has a name, the quark model. It was proposed independently in 1964 by Murray Gell-Mann and George Zweig. And in the 1960s, Gell-Mann organized the known particle zoo into a pattern called the Eightfold Way. It wasn't just a filing system, it was a prediction engine. The Eightfold Way had a gap in it, a slot where a particle should exist, but hadn't been observed yet. Gell-Mann calculated its mass in advance and called it the Omega minus. In 1964, physicists at Brookhaven found it, almost exactly where the math said it would be. That single discovery changed everything. It proved the quark model wasn't just a clever way to sort particles after the fact. It could tell you what was still missing from the universe's inventory before anyone had seen it. Then, in 1974, physicists discovered a 4th quark flavor, charm. And that discovery opened up a whole new set of predictions. If 2 charm quarks could bind together with a single lighter quark, you'd get an entirely new class of particle, a doubly charmed baryon. The math said there should be exactly 3 of them, the CCC++, built from 2 charm quarks and an up quark. The CCC+, built from 2 charm quarks and a down quark. And the Omega CC+, built from 2 charm quarks and a strange quark. 3 particles, predicted on paper in the 1970s, and for the next several decades, not one of them had been confirmed. The problem wasn't the theory. The theory was solid. The problem was that nobody had a machine powerful enough, or precise enough, to actually catch these particles in the act. Doubly charmed baryons are heavy, roughly 4 times the mass of a proton, and they're violently unstable. They exist for less than a trillionth of a second before decaying into a cascade of lighter particles. To find one, you don't look for the particle itself. You look for its wreckage, and then you work backward, reconstructing what must have collided and decayed to produce that exact pattern of debris. In 2002, an experiment called CELEX, based at Fermilab in the United States, claimed to have spotted the CCC+. It was a huge announcement, and then nobody else could confirm it. Other experiments searched the same mass range and found nothing. The claim sat in limbo for over a decade, neither fully accepted nor fully dismissed, a ghost in the data. The real breakthrough needed something CELEX never had, the Large Hadron Collider. The LHC smashes protons together at energies far beyond what any previous accelerator could reach, and it does this billions of times per second, generating an almost unimaginable volume of collision data. Buried inside all of that noise, occasionally, 2 charm quarks would be produced close enough together to bind. In 2017, the LHCb experiment, one of 4 major detectors positioned around the LHC ring, announced the confirmed discovery of the CCC++. This was the first doubly charmed baryon ever observed with certainty. 1 down, 2 to go. finding the second member of the triplet took almost another decade. It required not just more collision data, but a fundamentally upgraded detector, new tracking systems capable of reconstructing particle trajectories with far greater precision, because at this level, missing a decay by fractions of a millimeter means missing the discovery entirely. In March 2026, LHCb confirmed the Xi-CC+. The second slot in the family was filled. That left one particle standing between physicists and a complete set, the Omega CC+, the version built with a strange quark instead of an up or down quark. And on June 3, 2026, at the Beauty 2026 conference in Maastricht, LHCb announced they'd found it. The signal showed up as a distinct peak in the mass spectrum of its decay products, exactly where the quark model said it should be. 52 years after it was first predicted on paper, the triplet was finally complete. So why does this matter beyond simply checking a box? Because these three particles, taken together, are one of the best laboratories physicists have ever built for testing the strong force. Here's the key insight. The strong force is famously difficult to calculate directly. The math behind it, called quantum chromodynamics, or QCD, becomes almost impossibly complex once you have multiple quarks of different masses interacting in complicated ways. But doubly charmed baryons simplify the problem. With two heavy charm quarks doing most of the work and one lighter quark orbiting around them, the system behaves a bit like a miniature solar system, rather than three equally chaotic bodies. That makes it dramatically easier to model. By comparing the exact masses and lifetimes of all three baryons in the triplet side by side, physicists can now stress test their predictions about how the strong force behaves in ways that were previously out of reach. Every measurement is a chance to catch QCD getting something wrong, and so far, remarkably, the numbers are lining up with theory. There's also a broader point buried in all of this. This discovery isn't just about one exotic particle. It's proof that a mathematical framework built more than 50 years ago, using tools and understanding far more limited than what we have today, correctly predicted the exact contents of a class of matter before a single example of it had ever been seen. That's an extraordinary track record for any scientific theory to hold across half a century of increasingly precise experiments. And the story doesn't end here. The quark model doesn't just predict doubly charmed baryons. It predicts doubly bottom baryons, built from two bottom quarks instead of two charm quarks. It predicts mixed baryons, containing one charm quark and one bottom quark together. None of these have ever been observed. They're rarer, heavier, and even harder to produce and detect than what LHCb just found. But as the LHC continues its upgrade program and keeps accumulating data at higher intensities, physicists expect these particles to eventually surface too, filling in the next layer of a periodic table of matter that's still, even now, not entirely finished. What's wild is that we're living through the completion of a prediction made before most of our parents were born. If a theory can tell you exactly what's missing from the universe, decades before you can build a machine good enough to check, what else has already been predicted that we just haven't found the tools to see yet? Drop your guess in the comments. I'll pin the best ones. If you want to understand how physicists actually reconstruct an invisible particle from a trillionth of a second flash of decay debris, that's next week's video, so subscribe if you don't want to miss it. And if this kind of deep dive into the hidden architecture of matter is your thing, hit like. It tells me to keep making more of these.